Enthalpy is total heat content of the system, that is H is equals to U plus P into V. And here change in enthalpy delta H is equals to here delta U plus P delta V, or delta U plus delta N RT. By using this, delta H is equals to HP minus HR. Now here HP is greater than HR, that is delta H is equals to positive, that is endothermic reaction. HP is less than HR, then delta H is equals to negative, that is exothermic reaction. So based on this endothermic and exothermic reaction, to explain the spontaneity, here enthalpy heat content required, that is a change in enthalpy required. By using this enthalpy change, if delta H is equals to negative, that is a exothermic reaction, that is considered as a spontaneous. If delta H is equals to positive, that is a endothermic reaction, that is called a non-spontaneous process. Okay, but by using some chemical processes, yesterday explained, in last class explained about this change in enthalpy to explain spontaneity. Delta H or enthalpy factor is not only one factor to explain the spontaneity, to explain the criteria for spontaneity of the reaction, because some reactions cannot accept this concept, like ice is there, that ice is a solid. When exposed to the atmospheric air, it converted into a water liquid. Without any external aid, that ice water solid is converted into a liquid. Now by absorbing some amount of heat, ice converted into water, it is an endothermic reaction. Endothermic reaction, according to this concept, non-spontaneous, but it is not a non-spontaneous. It is a spontaneous process. So like some important contrary points are there to explain spontaneity by using this delta H. Okay, yesterday explained to you. So here along with the heat content enthalpy change, to explain spontaneity, one more important factor is introduced, that is disorderness or randomness. Your randomness or disorder. By using randomness of the process or disorder of the process, we can explain the spontaneity, that is under the name of entropy. Okay, now generally a process takes place in a closed vessel. This is a closed vessel. Now it is connected with one valve. That valve is just fitted with a simple connector valve. Yeah, take noble gas, gas 1, your gas 2, noble gas. Take your the two separate gases in separate vessels. Just this is one system, closed vessel, isolated system. Just valve is open to it. These gas molecules are entered into this, and these gas molecules are entered into this. Both are mixed, merged. Disorderness or the randomness of this gaseous molecule increases. Then what is randomness or the disorderness? Generally, in solid, all the particles are perfectly arranged. There is no disorder. Particular order is there. All the molecules are orderly arranged. It is a solid. Whereas in liquid, molecules are not a particular definite order. There is something disorder is there. So here the molecules are irregular order. This is the liquid. Whereas in case of gas, molecules are irregular. There is no particular order. Here, due to the strong attractive forces between the particles in solid state, all the molecules are tightly packed, they are regularly orderized here. That's why here disorderness or the randomness is 0 at absolute 0 kelvins. From solid to the liquid, here between the molecules, particles, interactive forces decrease, length increase, randomness increases, entropy also increases. Then again, your liquid to gas, again molecule distance increase, freely randomly moves in all possible direction, entropy again increases. Other randomness, disordered increases. That's why here solid to liquid, entropy, disorderness increase, again liquid to gas, entropy again increases. That's why here at 0 degrees or 0 Kelvin, absolute Kelvin, here the entropy of solid is 0 because all the particles are regularly arranged. Its entropy is 0, absolute 0, 0 Kelvin. That is one of the most important law. I will explain that law is third law of thermodynamics. According to third law of thermodynamics, absolute 0 kelvins or 0 degrees Celsius, the perfect crystalline solid entropy must be equal to 0. This is the third law of thermodynamics. Third law of TD, this is thermodynamics. So anyhow, here the total universe, system and surrounding system, disorderness or the randomness increases when the process is a irreversible, not a reversible process. So are the solid to liquid, liquid to gas, entropy of the randomness or disorderness increases. Whenever the randomness increases, it means temperature of the system rises or heat absorbed by surroundings. System contains some particles between molecule bond strength decreases and molecule freely moves randomly in all possible direction. Disorderness or the randomness increases, entropy of the system increases. That's why here the entropy is generally denoted by a symbol S. S is the measure of randomness. Measure of randomness or the disorder. Disorder is called a entropy. Now here the change in entropy is denoted by a symbol delta S. That is in a physical process S2 minus S1. In chemical process we can use SP minus SR. Entropy of the products minus entropy of the reactants. So this is in chemical process. This is in physical process. Now it is the change in entropy. Once we can observe this change in entropy, it depends only on initial and final states. That's why here the change in entropy is a state function, and it is an extensive property of the system. Extensive property. Here it is a state function because it depends only on initial and final state, and also it is an extensive means it depends on quantity or the amount of the substance present in a system. So by using change in entropy delta S, so we can define change in entropy of the system or universe or surroundings, it is the integrals of heat exchange. Yeah, the change in entropy is defined as integrals of heat exchanged divided by heat exchanged by the system divided by temperature. Now here ds is equals to 1 by T into integral dq heat. This is according to this integrals of the heat exchange under there is a change in the heat divided by temperature. Now here by integrating this we will get delta S is equals to, now here the Q divided by T. This is in a reversible process. So this is the mathematical form of change in entropy. This is also called a second law of thermodynamics mathematical form. Your mathematical form of second law of thermodynamics. What is state second law of thermodynamics? I will explain. Now here the delta S change in entropy is equals to Q reversible by temperature. This is T. Now by using this, here units for change in entropy is joules per Kelvin per moles, because your heat is expressed in joules or calories by kelvins. That is calculated under per mole. That's why here the units, SI units of delta S, that is SI system, is equals to joules per Kelvin per mole. Important units for change in entropy of the system. Now the change in entropy of the system delta S is equals to joules per Kelvin. According to this, entropy of the universe, change in entropy of the universe is equals to the change in entropy of the system plus change in entropy of the surrounding. This is also called a change in entropy of the total. Total means universe. That is. So the change in entropy means disorderedness or the randomness of the universe, means we can consider both in system and surroundings. That's why we can take. By using these, here delta S total is equal to 0 for reversible process. Reversible process, this is. Okay? Because reversible means reactants can be converted to products, products can be converted to reactants. Or here the system to surroundings, surrounding to the system. That's what this is. Now, according to this, delta S system plus delta S surroundings is equals to 0. Delta S system is equals to minus delta S surroundings. We know delta S system or delta S surroundings, we know delta S system is equals to Q reversible divided by T. Delta S surroundings is equals to minus Q reversible by T. This is because here minus sign. Now, if we can consider the system for an reversible process, we can take this value system. For an irreversible process, second case, for irreversible process, delta ST is greater than 0. This is for irreversible process. irreversible process. Its total change in entropy of the universe or total is greater than, because irreversible means process cannot reverse at any instant of time. Yeah, the system converted into surrounding or surrounding converted into system in one way only. That's why it goes on increases. So by using this irreversible process only, here one important second law of thermodynamics introduced, that is, all spontaneous processes are irreversible and tend to attain equilibrium. So by using this, here delta S system plus delta S surroundings greater than equal to 0. This is in a irreversible process. This is in a reversible process. Now, based on these simple expressions, based on this simple expression here, 2000, I think 12 or 13, one important example given. Which of the following is the correct expression for change in enthalpy? I'll derive in simple derivation, then I'll show the spontaneity based on this change in entropy and change in enthalpy. Then we'll introduce a new important factor, that is G, free energy. So by using this change in entropy in a reversible and irreversible process, in a reversible process, we know delta S system is equals to Q reversible divided by T. We can write T delta S is equals to Q. This is, we can write. According to first law of thermodynamics, we know change in internal energy delta U is equals to Q plus W. Now here the delta U minus W is equals to Q. Now we know external pressure at constant pressure, mechanical work done in an isothermal reversible expansion, delta U, this value we know, minus of minus P delta V is equals to Q. Instead of this Q, substitute here this value. P delta S is equals to delta U plus P delta V, this is. Okay. Now, according to the heat capacity at constant volume, CV is equals to delta U by delta T at constant volume, we know. R for N moles means NCV. Here NCV delta T is equals to delta U. Instead of this delta U, we can write this value. All these are derived in previous classes. Now here we can write T delta S is equals to NCV delta T plus P delta V. We know PV is equals to nRT for N moles. Here P is equals to nRT by V. Instead of this value, substitute here. Now that is NCV delta T plus, here instead of P we can write nRT by V delta V. Now by using this throughout divided with the help of T temperature, then your delta S or ds is equals to NCV dt divided by T plus nRT divided by T into V dV. Now T get cancelled. So integrating this reaction with respect to the corresponding terms, temperature and volume, we'll get to an important simple derivation by integrating the above equation. Our delta S is equals to NCV is common, integral T1 to T2 1 by T into dt plus, now here the NR into integral V1 V2 1 by V into dV. this expression integration. Now this is, we can write NCV, integral 1 by x into dx is equals to ln x, that is ln t, t1 t2 plus nr ln v1 to v2. This is, now this is, we can write NCV. This we can write directly. I'll write here log base c t2 by t1 plus nr ln base c v2 by v1. This is the change in entropy in a reversible process. Very, very important expression, given already one year in NEET examination. Here we know, according to ideal gas equation, P1 V1 by T1 is equals to P2 V2 by T2. This is. Now, instead of this V2 by V1, take here V2 by V1 is equals to P1 T2 divided by T1 into P2. Instead of this value, substitute here. That is NCV ln base c T2 by T1 plus nr ln base c P1 T2 by T1 P2. This is. So this is a log A by B formula. Again log A into B formula. We can separate it. We can write like NCV ln base c T2 by T1 plus nr. Here we can write P1 by P2 plus nr ln base c T2 by T1. Here T2 by T1 log, T2 by T1 common is, that's why we can take NCV. Here take NCV. Here NCV and nr common, take common, like n plus r into log base c T2 by T1 plus nr into log base c P1 by P2. This is. So instead of this, we know already here Cp minus Cv is equals to R. Cp is equals to Cv plus R. Instead of this, we can write Cp instead of this. That's why NCP log base c T2 by T1 plus nr log base c P1 by P2. This is a very, very important expression with respect to pressure. Two important expressions are very, very important. Okay. So these are the change in entropy in a reversible process with respect to volume, with respect to pressure. Clear? So by using these in a reversible process, total entropy is equals to 0 system and surroundings, whereas in a irreversible process is greater than equal to 0. So are the change in entropy in isothermal process. Isothermal process. Isothermal process means delta T is equals to 0, delta U is equals to 0. Okay. We know already first law of thermodynamics, delta U is equals to Q plus W. In isothermal process, this value equal to 0. That's why 0 is equals to Q plus W. Now here the Q is equals to minus W. We know change in entropy, delta S is equals to Q by T. This is, or T delta S is equals to Q. This value we know. Here minus W. Already we know work done, W is equals to minus 2.303 RT log V2 by V1, or minus 2.303 RT log P1 by P2 according to mechanical work done. We know this is. So instead of W, we can write here minus or minus plus That's why your 2.303 RT. Take nRT. This is here also nRT log base 10 V2 by V1. This is T delta S. Now here we want change in entropy. Delta S is equals to rho divided by T 2.303 nRT divided by T into log base 10 V2 by V1. TT get cancelled. Now it is 2.303 nR log base 10 V2 by V1. This is also we can write simply nR log base E V2 by V1, or also 2.303 nR log base 10 P1 by P2. This is nR log base E P1 by P2. This is very, very important, already given in NEET examination derivation. Which of the following is the correct change in entropy of the system? So finally, by using all these, we can easily express by using change in entropy. Entropy of the system or the universe goes on increases. Goes on increase means product side entropy is maximum. That's why here always entropy change always positive in an irreversible process. That's why your delta S is equals to S2 minus S1. If S2 is greater than S1, that is delta S is equals to positive. That is called a spontaneous process. If S2 is less than S1, then delta S is equals to negative. That is non-spontaneous process. Just like delta H is equals to negative, that is spontaneous, and delta H is equals to positive, that is non-spontaneous processes. But here by using alone change in entropy, we can't explain the spontaneity of a chemical processes, because for exothermic processes, here from system to the surrounding heat is liberated. Means initially it is S1, it is S2. Finally, what happens? System initial value, system to the surrounding, finally S2 value increases, S2 is more. That's why here delta S is equals to positive, spontaneous. Process is exothermic. Exothermic means delta H value is negative, but delta S is positive. It is not delta H, delta S for exothermic process. For exothermic process, delta H is equals to negative, but delta S is positive, because from system to the surrounding, your disorderedness increases. Heat by decreasing the heat or by disorderedness decreases from system to the surrounding. This value is more, disorderedness is more than compared to here. Delta S is positive. That's why it is a spontaneous. Again, if surroundings to the system, then it is S1 and it is S2. In this case also, delta S is equals to positive for endothermic process. So here for both endothermic and exothermic process, delta S is positive. That is system to the surrounding and surrounding to the system, disorderedness increases. That's why by using alone, we can't decide its spontaneity. By using alone, instead explain delta H, we can't decide its spontaneity. That's why another important third term introduced by Gibbs scientists to explain clearly spontaneity of a chemical or the physical processes. That is third important factor. That factor is, third important factor is free energy. Free energy is denoted by G, or this is energy factor. Energy factor. It was introduced by Gibbs scientist. That's why this is called a Gibbs energy, denoted by symbol G. So here the free energy or energy factor, Gibbs energy, is the amount of energy required to do the useful work. So the useful work means to throw the chalk piece, some amount of energy required to me. That is useful work. So from system to the surrounding, or from one process initial to the final process, amount of energy required to do the useful work, while doing some amount of work, amount of energy is decreased. From initial to the final state, amount of energy is decreased. That's why here initial to final, it depends. That's why free energy also a state function and is an extensive property of the system. By using this, here free energy is equals to G is equals to enthalpy of the system minus product of the temperature and entropy. It was introduced by Gibbs scientist. It is a Gibbs equation, energy equation. Here G is equals to H minus T into S. If we can write G is equals to H, there is no meaning here, because already enthalpy is the heat content. And G is also energy. There is no difference. That's why Gibbs created one more important new mathematical expression to explain the spontaneity. That is G is equals to H minus Ts. The product of T and S, temperature and entropy of the system or the surroundings, or the total, that is. Now by using this here, initially this is denoted as G1 is equals to H1 minus Ts1. Temperature remains constant. On final state, G2 is equals to H2 minus Ts2. To get the difference, equation 2 minus equation 1, that's why here the G2 minus G1 is equals to H2 minus H1 minus of T into S2 minus S1. This is the delta G is equals to delta H minus T delta S. This is the Gibbs energy change expression. Okay. Now here this is as H2 minus H1, this is minus T into S2 minus S1. Gibbs free energy change means that is delta G is equals to summation of energies of the products minus summation of energies of the reactants. Or also we can write here the delta G is equals to G2 minus G1. It depends on initial and final state. That's why it is a state function, and also it is an extensive property of the system. Clear? Now by using this, delta G is equals to delta H minus T delta S. Delta G is the change in free energy of the system while doing some amount of work. To do the useful work in this expression, this is very, very important. That is unavailable energy factor. Unavailable energy factor in Gibbs free energy change is T delta S. Already given in KCET examination once. In a Gibbs free energy change expression, the unavailable energy factor is T delta S. Useful energy is delta H. To balance that, introduce one important term, that is delta G is equals to delta H minus T delta S. By using this, one of the most important expression, if delta G is equals to negative, that is a spontaneous process. If delta G is equals to positive, that is non-spontaneous process. Delta G is equals to 0, the process is at equilibrium. These are three important cases, very, very important. Generally, a process is carried out at a constant temperature. Initially, the reactants energy or enthalpy, like HR. It is carried out in a closed vessel. Slowly, reactants converted into products, and again the products converted into reactants. There exists a equilibrium. This is now here HP. This is products. This is HP. Or energy of the reactant GR and energy of the product GP. This is means here the A plus B slowly converted into C plus D, and again C plus D converted into A plus B. Equilibrium exists. While converting reactants to products, chemical reaction, at certain state, that state is called a equilibrium state. At equilibrium state, G is minimum. G is minimum. So at equilibrium, here the G1 is equals to G2. Both are equal, because initial state and final state at equilibrium both are equal. So here the both are minimum. This is. That's why delta G is equals to G2 minus G1. G2 value minimum, G1 value also minimum. Both are equal. That's why here the minimum minus minimum, that is 0. Delta G at equilibrium must be equal to 0. Similarly, here delta H is equals to also 0. But here the H is equals to minimum. Enthalpy is minimum. Whereas entropy, S is maximum. S is maximum at equilibrium. So S is maximum at equilibrium, very, very important. But here the enthalpy and free energies are minimum, but S is maximum. What is S? Entropy. So at equilibrium, continuously reactants convert into products, products convert into reactants, cannot stop, just like a dynamic equilibrium. At this position, here the randomness increases. Randomness increase means entropy increase maximum. But here at equilibrium, S1 is equals to S2, maximum minus maximum. That's why at entropy at equilibrium, delta S is equals to S2 minus S1, maximum minus maximum. That's why 0. So finally at equilibrium, delta G is equals to 0, delta S is equals to 0, delta H is equals to 0, but here H, G are minimum, and here S is maximum. This is a very, very important list. And one more is, here delta G is equals to 0, but delta G not equal to 0. This is equal to 0, but delta G naught under standard condition, there are standard elements not equal to 0. That's why delta G naught under standard condition means that is at 1 atmospheric pressure and 298 kelvins calculated G value, delta G value is called standard free energy change. This is at equilibrium. List very, very important list. This is. By using all this, I'll create final spontaneity with the help of H, with the help of S, delta S. Final conclusion, this unit conclusion. spontaneity of a process, chemical or the physical process, using delta G, delta H, delta S and temperature. Very, very important list will create. One table will create. Now here by using signs of all the four important factors, spontaneity of the process. Already we know if delta G is equals to negative, that is spontaneous process. Delta G is equals to positive, that is non-spontaneous process. If delta G is equals to 0, that is at equilibrium process. Okay. Now the value of delta H, delta S, and here temperature, finally your delta G value and final conclusion. Final conclusion means spontaneity. Spontaneity of the process will create. Make for temperature column is somewhat big column, because there are 2 to 3 cases will get it here. We know delta G is equals to delta H minus T delta S, it is, we know. Okay. I'll take first case one is, I'll take this value is negative value, and here the delta S value I will take positive. Now your temperature, by using this temperature, once observe here, this is negative value, negative, and here delta S is positive, T into positive value. Your positive into negative, negative, total value negative. Negative means it is a spontaneous. Okay. That's why here the temperature is either low or the high temperature. That's why here at any temperature, this value is negative. It is a spontaneous process. Clear? Okay. Now here I'll take this value also second negative only. This is negative means exothermic process. Now this value I'll change. Here I'll take negative value. Now by using this, this value negative only, negative minus T into this value, here negative is there. Here this value is negative. Here the negative into negative positive, negative plus T value, something delta S value. So here the negative is there, positive is there. That's why your delta G value depends on T temperature. If the temperature is less, that is at low temperature, positive value is low, negative value is more, delta G is equals to negative, spontaneous. That's why here at low temperature, this value is negative, it is a spontaneous. Here only, same here negative. Here negative, third case. Here at high temperature, this value is positive. This is non-spontaneous. Because here temperature is high, positive value increase compared to the negative value. Delta G becomes positive. That is non-spontaneous. That's why for exothermic reaction, these three are there. So one is positive, another negative cases. The next I will take delta H is equals to your positive value, and I will take this value also positive. Now here this value is equals to positive minus t into this value also positive, positive into negative, negative this value, and delta H value is positive. So this delta G depends on temperature. Now at low temperature, low temperature, this value is low, negative value is no, this value becomes positive, that is non-spontaneous. Clear? That's why here at low temperature, this value is equals to positive because low minus value is less. That's why it is a non-spontaneous process. Same here, I'll take positive. Yeah, also this value is positive, but at high temperature means here negative value is more than compared to positive value. That's why this is negative. This is a spontaneous process. Here I'll take this value is positive. All the positive means it is an endothermic reaction. I'll take minus negative. Here last case delta G is equals to delta H minus T delta S. This value is positive minus also delta S value is negative. Here negative into negative positive, total value is positive at any temperature. That is non-spontaneous process. That's why at any temperature this value is positive. That's why it is a non-spontaneous process. This is very, very important table to explain the spontaneity by using exothermic and endothermic processes. Exothermic 3 cases, endothermic 3 cases. The value of delta G mainly depends on temperature. At any temperature, 2 cases are there. At a low and high temperature, 4 cases, 2 are in exothermic, remaining 2 are the endothermic processes. Okay, last 2 important, simple important expressions are there, direct relations. I'll write and I'll explain that, and I'll start some problems, previous year problems. So the relation between now standard free energy change, standard free energy change, and equilibrium constant, that is Kp. Now here we know delta G is equals to delta G naught plus 2.303 RT log base 10 Kp this is. In terms of pressure or in terms of concentration, like A plus B gaseous reactants gives rise C plus D gaseous reactants. Kp is the product of the partial pressures of the products and raised the appropriated powers like 1 divided by product of the partial pressures of the reactants. This is Kp expression. Now the process is at equilibrium. So at equilibrium process, delta G is equals to 0, but not delta G not equal to 0. Okay. So here better you take here 0 equal to delta G naught plus 2.303 RT log base 10 Kp this is. Or delta G naught is equals to minus 2.303 RT log base 10 Kp value this is. Or also we can write log Kp is equals to minus delta G naught by 2.303 RT Or Kp is equals to, we can write 10 to the power minus plus delta G naught by 2.303 RT. This is a very, very important relation. If it is in log base E, that is, we can write Kp is equals to minus delta G naught divided by RT. This is. Here Kp is equals to e to the power delta minus delta G naught by RT. Here also, but you take minus. These are the two important relations for Kp, equilibrium constant. Okay. This is the relation between standard free energy change and equilibrium constant. And one more important last relation. In second year electrochemistry, there is an important relation between standard free energy change and EMF of the cell. So the standard free energy and EMF of the cell, that is electrical work done, delta G naught is equals to minus NF E naught cell. This is. In second year electrochemistry, last there is an important relation based on Nernst equation. Here it is EMF of the cell, it is Faraday. 1F is equals to 96,500 coulombs. N is number of electrons transferred. E naught cell is equals to EMF of the cell. E right hand side electrode minus E naught left hand side electrode. We know already delta G naught. This is the delta G naught expression. We can relate with that. That is, delta G naught is equals to minus 2.303 RT log Kp is equals to minus NF E naught cell. So in this we can calculate any one. Minus minus get cancelled. E naught cell we can calculate, or equilibrium constant we can calculate. Because here by using equation, we'll get N value, and this is constant, temperature value, this is constant. Main relation is Kp and EMF of the cell. Okay, this is the one of the most important relation between standard free energy change and EMF of the cell, and also equilibrium constant and EMF of the cell. So maximum in 7 to 8 classes, complete synopsis explained to you. In thermodynamics, in previous analysis and NEET examination, maximum from thermodynamics, maximum will get 2 questions. Guarantee 1 question, minimum 1 question, maximum 2 questions. So without any mistake, without any negative marking method, read thoroughly synopsis and follow these videos. And max very simple questions they'll ask based on thermodynamics. If they'll give luckily 2 questions, 8 marks will get it. So anyhow, nearly 15 to 20 different questions already given to you previous years. We'll solve one by one. Already some 5 to 10 questions solved. Remaining questions I'll solve now. And remaining questions, any balance questions are there? Remaining tomorrow I'll solve it. First, okay, my dear students, 2006 NEET 2006 question. Identify the correct statement for the change of the Gibbs energy of a system at constant temperature and pressure is. Just now explained to you. Here, identify the correct statement for the change of a Gibbs energy. Gibbs energy change, identify here what? At constant temperature. It is NEET 2006 question based on this first question here. At constant at constant temperature and pressure at equilibrium, what is the nature, the state of this delta G? What? Equilibrium. At equilibrium, delta G value is what? 0. The same in third option, if delta G system is equals to 0, the system has attained equilibrium. That is the correct answer. Now here this value is equals to 0, that is equilibrium. Negative, that is spontaneous process. Positive, that is a non-spontaneous process. Very simple question from thermodynamics. Now clearly thermodynamics 7 to 8 classes without any tense, very clearly explained, only one chapter, 7 classes. Better solve all these models, will get the all questions in public 2020. Also will get the 2 questions, 8 marks, no doubts. Now second question, assume each reaction is carried out in an open container, for which reaction will delta H is equals to delta E. There is a good relation. Second question, this is also a 2006 NEET. Your delta H is equals to delta U when given 4 option, or delta H is equals to delta U, whatever. Right? We know delta H is equals to delta U plus delta N RT, or delta U plus P delta V. When these are equal, 3 cases very clearly explained. It was very clearly explained while explaining the derivation between delta H and delta U. If delta N is equals to or delta V is equals to 0, then delta H is equals to delta U. Now this delta N is equals to number of gaseous products minus number of gaseous reactants. So identify the given 4 options. Second option is H2 plus I2 gives to HI. This is a gas, 1 mole here, 2 moles, this is also a gas. Delta N is equals to 2 minus of 1 plus 1. Here N1 is equals to 1 plus 1 because these are the gaseous. Here N2 is equals to 2, that's why this value is equals to 0. That's why delta H is equals to delta U. That's why second option is the correct one. Once we can observe remaining options, first option, third option and fourth option, values are in remaining options delta N value not equal to 0. They are either maybe a greater than 0 or less than 0. In such cases, delta U not equal to delta H, either maybe a greater than delta U or less than delta U. Remaining cases. Okay, next. Third one is enthalpy and entropy change for the reaction Br to liquid given, Cl to gas given, to BrCl gas given, values given. The temperature at which the reaction will be equilibrium is. So the third one is 2006 only, NEET 2006 only. We know delta G is equals to delta H minus T delta Es. Now they are in equilibrium, delta G is equals to 0. In such case, delta H is equals to T delta S. Now at what temperature they are in equilibrium position? So by using the equilibrium, delta G is equals to 0, we know the formula like this. Now that is delta H divided by delta S. Now the delta H value given here, your enthalpy and entropy changes given. This value is 30 kilojoules per mole, and this value is 105 joules per mole. So just observe the thing, how it confuse the students examiner here. Now this value is in kilojoules, but delta S is only in joules. That's why compulsory convert it is in kilojoules or it is in joules. That's where the 30 into 10 cube joules per mole per mole, and this is entropy given. That entropy is 105 joules per Kelvin per mole. Per mole cancel, joule cancel. This is Kelvin. We'll get it. Answer is here. Okay, 30,000 divided by 105. Nearly we'll get 285.7. Next one is okay. Next remaining 4th, 5th, and 6th, 7 already explains based on bound energies. Tomorrow I will complete remaining all models, and expected model also will guess it next year, 2020 model. Then we'll start a new chapter. Okay, take care. Thank you.